generation of mechanical tests to test materials at high strain rates. And it is based on the modern capacity of ultra-high-speed imaging. And I will say a little bit more about what I mean by ultra-high-speed imaging in a few minutes. Just want to acknowledge my co-author, my main co-author. You will see other names in the presentation, but this is really teamwork. So Dr. Lloyd Fletcher was instrumental in developing all the hardware and some of the analysis techniques presented here. So he now works at the UK Atomic Energy Authority, which is the UK fusion energy lab. As for me, I also now work for a company called MatchID, which is a company I created with colleagues in Ghent, in Belgium, and we are developing digital image correlation platform with integrated post-processing. But I also work still part-time at the University of Southampton, and all the work here was actually done at the University of Southampton. So the talk will be organized as follows. I'll give a brief introduction, and then I will spend time in giving you the underpinning ideas on what I call the IB test series. IB means image-based, and you will see why. And then I will detail 3 applications, 3 different configurations arising from that underpinning ID. The image-based inertial impact test, the image-based ultrasonic shaking test, and the image-based inertial release test. And you will see that they consist in different ways of inputting the deformation energy in the specimen to obtain high rate deformation. I will then give a few words of conclusion. So I guess you're probably all convinced that materials generally behave differently, whether they are loaded slowly or rapidly, and that's because of a number of relaxation mechanisms happening at the scale of the structure of the material. So there are a few examples here of things that deform fast, from the golf ball all the way to, on the right-hand side, this is orthogonal cutting. So machining operations generally lead to very, very high localized strains and strain rates in the workpiece. And so to address that behavior, we need specific test methods to do that. If you look at the gold standard currently in this field, is the so-called Kolsky bar, or split Hopkinson pressure bar. It's sort of named, so it consists in sandwiching a test piece in white here between 2 bars instrumented with strain gauges. And if you look at the history of it, the first idea of using elastic waves in a bar to evaluate a loading pulse dates back from Bertram Hopkinson, and the first paper was published in 1914, sorry, doesn't make us any younger. But the arrangement that you see here was actually developed by Herbert Kolsky, and the paper is 1949. So for those of you who see Gérard Gary often, he's also played a very important role in this area. So he's the local guru of Hopkinson bar, and he's particularly well known for extending the capabilities to the use of viscoelastic bars to have the possibility to measure smaller efforts. So this technique is great, and it's been used extensively over the past decades to obtain high strain rate behavior of materials, but it does suffer from a certain number of drawbacks. And one of the major drawbacks that it suffers from is the fact that the analysis to obtain the material properties from the reading of the bars does rely on the assumption that the specimen is at quasi-static equilibrium, meaning that the forces on each side of the specimen are equal in magnitude and opposite in sign, of course. So if you write the full equilibrium of the test specimen, in fact, what you know is that the sum of these forces is actually equal to the integral of the density. So I've taken it out of the integral here, assuming that the density is constant, but it should actually probably better to put inside the integral. Times the acceleration here, so the longitudinal A1, the longitudinal component of the acceleration, integrated over the whole volume. And of course, when inertia effects damp out, then this term here becomes 0, and you recover the quasi-static equilibrium, which is sum of forces equals 0 at both ends. So this assumption has drawbacks in particular cases, generally in quasi-brittle materials. So things that deform very little, and that you might reach damage or fracture before you can establish that quasi-static equilibrium. Particularly if you look at carbon epoxy or glass epoxy composites. in the 90-degree direction. So when you have the fibers running perpendicular here to the load line, then you have very low strain to failures in tension. And you also have generally low wave speed, a couple of kilometers per second. And so if you look at the data in the literature, generally it's quite poor in the elastic range. So I've picked up here a curve that I got from that paper here by Amos Gilad and his co-authors, where you can see here a stress strain curve for a 90-degree composite. This is the quasi-static response here, nice linear, nice line. It's quasi-brittle, so you load fracture and then the load just drops with a macroscopic crack. And that's for small strain rates. That's all obtained on the test machine, on the tensile test machine. And then going to higher strain rates, 400 per second, this is obtained on a split Hopkinson bar, and you see that the curve is actually quite ugly. And also, if you look at the initial stiffness, this predicts quite a large increase of the initial elastic stiffness. And this is a thermal set, which doesn't actually have that much of a rate-sensitive modulus. So this is most certainly an artifact from this procedure. But you see the curve is quite messy, and you have a change of slope here. So this is not very good data. And this is rather characteristic of what you find in literature. There's actually not that much data on 90-degree composites, probably because people don't even try now to obtain such data, because it's very, very difficult with this setup. So we are trying to use opportunities in the development of digital imaging, and particularly high-speed digital imaging, to revise this test method and try to see what we can do. If we can now measure the map of deformation of the specimen in a time-resolved way, maybe there are different ways of designing a test and processing the data that makes use of this wealth of information compared to the times where we only had strain gauges. So that's the philosophy behind the research. So I was fortunate enough to land a big project funded by EPSRC, which is the British equivalent of ANR, for 5 years, where the job was to investigate, to explore the design space for new test methods based on this. Before I start, I want to thank my collaborators. Of course, this is a massive group work, even though I was leading it, but all the nitty-gritty was done by a number of people, so PhD students, postdocs, and most of them are here on this slide, apart from my main co-author, Dr. Lloyd Fletcher, who was really instrumental in most of what I'm going to present. Okay, so what is the idea behind this IB test series? So this is what I'm going to focus on now. So these are three configurations. There's probably many more you can invent, because you can be quite creative. But these are the three that we came up with, sometimes accidentally, like for the first one, the third one, or sometimes the first one was really what we had in mind initially. The first one is rather intuitive. It's very similar to a Hopkinson bar setup, except that you don't have an output bar. So in a way, it's still similar to polling tests on brittle materials. We use very short pulses generally here, on the order of 20 microseconds. So we put all the energy in one go by an impact. Another way you can put the energy on is by putting it in cyclically. And to have enough high rates, then we use ultrasonic frequencies. And in that case, if you use tens of kilohertz of excitation, you can establish vibration, either established variation or progressive waves. That will deform the material in the tens to hundreds of per second. The third one is the so-called image-based inertial release. So that was again done accidentally. We were collaborating with some people who wanted to look at the wavefront generated by a material fracture. But then we sidetracked the test there. We can also have material properties from that. So I'll present that at the end. I will spend most of the talk on the first one, because this is where we had the largest number of applications. The underpinning idea of all these tests is that you will use the field of acceleration as an embedded load cell. So let me just explain. So this is the typical configuration actually for all three tests. But imagine that this is the IB test. So you have an impact here, F of t. So you're hitting the side here of the specimen, and you have a wave traveling through this. If you isolate the subsystem in blue here, you could show by very simple equilibrium, so force is mass times acceleration, basically, that the average stress in the one direction, average over that cross section here in red, is simply equal to the density of the material, the distance to the free edge, and the spatial average. The bar here indicates a 2D averaging of the acceleration A1 over the blue area here. So between the free edge and the section you consider. And this is valid for any section along the length of the material. Okay, so that's just simple equilibrium. Obviously, to have that, you need to be able to obtain full field deformation. So you need to have a spatial information on the acceleration, but also with sufficient temporal resolution, so you can differentiate the signal twice to get meaningful acceleration. So I'll say a few words about that later. But now, of course, because you have this average stress here, and you can also, if you have full field displacement, you can obtain strain as well. So you have acceleration on one side, which gives access to stress, strain on the other side, and then you can construct stress-strain relationships and start saying things about the constitutive behavior of your material at this kind of rates. This is actually a very simplified method of a more generic technique that I spent a long time designing ever since I started my research career. It was initially really devised for quasi-static loading, and we only went into dynamic loading the last 10 years, but it's called the virtual fields method. I don't really have time to go into this today, but just know that this is a very simplified version of the virtual fields method. Interestingly, these equilibrium equations, you can derive two others, because here I've just described the equilibrium projected on the horizontal axis, but you can also project it on the vertical axis. And in that case, you get an average of the shear stress, sigma 1, 2, on that red section, as a function of the average of the vertical component of the acceleration. Okay? So that gives you the average shear stress in that section. And if you look at the rotational equilibrium of the section, you can then devise what we call the linear stress gauge, for want of a better word, but it's what we called it among ourselves in the group. So hence the notation LSG for linear stress gauge. And this is composed of two terms. The first term is the stress gauge, so the constant stress, or the zero order moment, if you prefer, of the stress, plus a linear term, which you can see here, which contains the density, the position to the free edge, the width. Here, you have weighted average of the acceleration, so A1 and A2, weighted by the position of the point in the field of view, but it's still very easy to calculate, and X2. So now we have a linear variation of the stress. So this corresponds to the first moment of the stress, sigma 1, 1, that we get from acceleration. Interesting to note that these three measures, so sigma 1, 1 LSG, sigma 1, 2 bar, or sigma 1, 1 bar, they all derive only from acceleration, and so they totally ignore the constitutive behavior. So you have a stress metric that is totally independent from the constitutive behavior. Okay? So that's always valid, regardless of the material you're considering. So if you want to exploit that, what you need now is you need to be able to calculate this. This needs time-resolved measurements, space-resolved and time-resolved. So you need to be able to image the deformation of your specimen with a camera that is fast enough. If you look at the orders of magnitude, if you look at the typical wave speed in a material, it's the square root of Young's modulus divided by the density. If you take a carbon epoxy quasi-isotropic, for instance, with a modulus of 45 gig and density a bit less than 2, then it gives you a wave speed of 5 kilometers per second. In other words, every microsecond, your wavefront advances by 5 millimeters. So if you want to capture that, it means that you need to resolve below the microseconds, ideally. Okay? So that's super fast imaging. And you need to do it in a way that you have enough pixels, so you also have spatial information. Okay? Until a recent past, this was not possible with enough image quality to be able to do quantitative imaging. If you look at the rotating mirror cameras, for instance, like the coding cameras, very, very hard to make precise measurements with this, certainly not in the elastic range. If you look at gated intensified cameras, same thing, too much blurring caused by the image intensifiers. So it's only with the new generation of ultra-high-speed camera based on in-situ image storage. So the images are stored directly on the chip. So you avoid the problem of memory readout, that you can reach the kind of specs that you need to use these new test methods. So this camera, Shima 2 HPVX, HPV stands for hypervision, has a specific sensor. It's called fast transfer CMOS, which gives you 400 by 250 pixels, but regardless of the speed. Okay, and it goes up to 5 million frames per second, so 200 nanosecond interframe time. This means if you look again at the wave speed, 5 kilometers per second, it means that between two images, your wave will have advanced by 1 millimeter. Okay, so you can really see the wave, the elastic wave, move at slow motion with this kind of frame rate. Unfortunately, there's only that much space on the chip, and you only get 128 images in a film. Okay, and that's because of the physical space you have on the chip to store the images. So you store the images directly on the chip, you get 128, the test stops, and then you transfer, after the event, you transfer the images onto the computer. That's how it works. Okay, so this is the underlying idea of this IB test series. I'm now going to look into particular applications, and I will start with the IB test. So the IB test is basically just an impact test. So we don't need bars, like in Hawkinson bar. We just need to generate a pulse in the specimen. So we are sort of using bars, but very short ones. So we have the specimen here, which is flat. In plane dimensions vary depending on what you want to look at. Here, the example I'm going to demonstrate it on is a composite with fibers aligned in the vertical direction. Okay, so it's transverse direction, unidirectional composite. To hold the specimen and also smooth out the introduction of the wave, we use a waveguide, which has also the advantage of holding the specimen. So we put the waveguide on a foam stand. The specimen stands here, waiting to be impacted. And on the right-hand side here, you see the impactor, which is embedded in a polymer sabot to reduce friction in the gas gun. We could adjust the material of the waveguide and the height of the impactor, the length of the impactor, so we can have different types of waves. For some materials, we want very narrow waves. For some materials, we want longer waves. That depends what you want to do. So yeah, there's sort of natural pulse shaping embedded in this. This is the gas gun we built at the University of Southampton. It's very simple. It's just a very long barrel. To be honest, this is probably a little bit over-designed because initially we were not quite sure. The specs of the valve, of the servo valve, were very scattered in the data sheet. So we just wanted to be safe. I think you could, if you were to rebuild this now, we just use probably half a meter or maybe a meter of barrel. This is 2.5 meters. So it's actually quite long. A pressure vessel, an electronic valve here, and a system to release the pressure to launch the specimen, which travels along the barrel. It's quite a large diameter barrel. It's 50 millimeters in diameter because we want quite large impactor to have nice 2D waves in macroscopic specimen. This is the useful end of the gun. So you see here the end of the barrel where the projectile will come out. You see the foam stand, the waveguide. You see the two little wires here. These are used to trigger the camera. So when the projectile hits the waveguide, it closes the circuit here, sends a pulse to the camera, and then we delay the trigger of the camera by the time it takes the wave to travel down the waveguide. As you will see, when we do 5 million frames per second, the test only lasts about 24 microseconds. So in terms of triggering, you need to make sure you get it right, because it's very easy to miss the action when there's only 24 microseconds of it. There's an additional difficulty with the illumination, because this flashlight has a rise time of about 100 microseconds. So if you were to trigger the flash with the camera, you would have beautiful dark images that you couldn't exploit. So we have to pre-trigger the flash, which is fairly tender. And we have light gates at the end of the barrel that send a trigger to the flash. The flash has then time to rise, and then the wave comes in, we trigger the camera, And when everything goes well, we have nice images. Fortunately, we have built-in a little Arduino system that automatically reads the light gauge, calculates the delay, and so it's pretty much plug and play. We have very, very rarely misses in our test, thanks to that. So it's quite robust. So here the example I'm going to show, we're only imaging at 2 million frames per second because the wave is a bit slower. It's only 2 kilometers per second. The impact speed is typically between 30 and 40 meters per second. So it's not very, very high speed. But it's enough to create significant deformation. So this is the mobile phone version of the test. You see the, I think it's going to replay. The waveguide here, the specimen, and then the projectile hits from the right-hand side, and then the whole thing just flies off in the capture chamber, and the waveguide bounces back and forth. And if we're lucky, we can reuse it. If we're not lucky, then we have to 3D print another one. But that's basically how it works. It's not very interesting here. If you zoom in time now with the Shimatsu camera, so this is a typical film obtained with the Shimatsu camera. So if you look carefully, you see at the beginning, the wave comes in, but this end doesn't move. Then the wave reaches the end and it's pulling on the material. What happens is that the compression wave bounces back on the free edge, turns into a tensile wave, and eventually fractures the specimen. You see here, these are 90-degree cracks along the direction of the fiber. And so it's the wave rebound that creates the tension. So you don't have actually to pull on the specimen. The waves do the job for you, which is quite clean in terms of boundary conditions. So here to measure the deformation, we don't use the IC. We use the technique called the grid method because it's slightly better in terms of the ratio between spatial resolution and resolution. At the cost of having to put a grid on, but we directly print it on the specimen using a flatbed printer, and that works quite well. The grid pitch is about 0.68 mil. And so from that, we can analyze the images, use spatial phase shifting to read the grids for deformation, and we get displacement. So here I'm going to show a video that shows on the top left the displacement. It's actually the displacement minus the rigid body displacement, so I can keep the same scale. Okay. On the right-hand side, you got the acceleration in the longitudinal direction. So I'll draw your attention to the scale here. The amplitude here is about 1 million Gs. So we create massive accelerations because the pulse is so short. Bottom left, you have the longitudinal strain. So here, if you look at the scale, it's plus or minus 2% of strain. This thing deforms significantly, particularly in compression, because it's quite soft. And here you have the strain rate, which is the time derivative of the strain with a scale on the order of a few thousands per second. So I'm going to play that video. And you see the wave coming from the right-hand side. This is the strain, compression strain. Then the wave reflects, goes into tension. And here, this is actually a crack opening. It's not a strain anymore. You can see it's going to play again. You can see the crack better on the displacement map. The wave rebounds, and then you start to see discontinuities here. These are cracks in the 90-degree direction starting to form. Okay. So what we can do now is we could use the stress gauge equation. I'm going to show data for that section, but remember you have data like this for every transverse section. Okay, so in a way we space with all of this information, but this is for this section where the first crack appears. You see at the beginning, nothing happens until the wave reaches this section. Then it goes into compression, unloads, goes in traction, and then the crack appears, and you have fracture. Okay, so it gives you a nice stress strain curve in this configuration. Very, very nice and linear. And I want to draw your attention to the difference of quality compared to the typical things you can find. I mean, I couldn't find better than this in the literature. But this gives you absolutely amazing quality of data in the elastic range at reasonably low strains. Now, this is interesting. We can calculate modulus from this. And in fact, you have the modulus for each section. So each row of data point or column of data points, you can calculate a stiffness. So this is a plot for 5 different specimens of a particular composite as a function of the position. So we remove data at the free edge because the strains are very small there. So we have large noise effect, so the data are not very reliable. And same thing at the entrance here, where we have 3D effects because of the loading. But if we take this represents about 75% of the specimen length. We have something that is fairly stable. You could see here a little bump. This is actually the witness of some out-of-plane effects, bending effects. So when the wave reaches the free edge, then the wave knows the specimen length, and you can start having bending effects. And so we found a way now to align our specimen better in the transverse direction, and this was published very recently. So the latest results, the new results we generate now don't suffer from that. In any case, it's still quite stable. Remember, it's space resolved, so it's actually quite challenging. If you take the average of this value over this length, for the 5 specimens that we've tested, you see an extraordinarily stable response with coefficient of variation here that would make anyone doing quasi-static test on this kind of specimens very jealous. So this was super reproducible. We have a slight increase of modulus from the quasi-static, but you see it's not actually that massive. It's about 15% or typically, but there's not large effect. We've tested thermoplastics, and in that case, you have much larger effects, sometimes ×2 between quasi-static and high rate. But this is a thermal set, it's not super sensitive to strain rate. What is interesting now is the fracture analysis. So can we get a fracture stress from that? It's a little bit more complicated now, because for that we need to space resolve the stress. And we can't really do that, but there's a way around it. So the first thing we do is we take the specimen, we calculate the strain from displacement, but without any spatial smoothing. You see, it's quite noisy. But the good thing is, you can pinpoint very easily the place and time when you start having a crack opening, because you have really a strain, which is a crack opening that shoots up. And so you can really localize this. And now, because you have the modulus, you can go from strain to stress by using the stiffness identified in the previous step. So you have a map of stress that is reconstructed from the strain. But the good thing is now we also have a map of stress that we can reconstruct from the acceleration independently. Okay? So unfortunately, we don't have the 2D map of stress. We can only have the first moment through the stress gauge equation. But if you can ensure that the actual distribution of stress is either reasonably constant to the width or reasonably linear, so if you introduce knowingly an angle between the impactor and the waveguide, so we try that, then your first moment is actually a good approximation of the actual stress. Now what you can do is you can calculate over this little area here where the crack appears, you can calculate stress from strain, stress from acceleration, and then you plot them both as a function of time. And what you see is the following. So in black here, this is the stress from acceleration, and in blue, it's stress from strain. What you see is at the beginning, the two match quite nicely. Okay, it goes in compression, reverts, unloads, goes in tension, and then at some point, you have a massive, very large departure of the two. And this is when your strain turns into a crack opening. And that's a departure from continuous behavior. And so that will give you an approximation of your failure stress at that particular point. Okay. And you can do that for all sections. If you have a crack that appears, you can redo the same analysis. Now, if we look at what happens on the different specimen, this is the failure stress as a function of the number of specimens. So 5 specimens tested again. You see there's more scatter now, which is not surprising because fracture is more defect driven. So we're not expecting as much reproducibility. There is also an uncertainty here that comes from the actual stress distribution. Okay, so that's something that's a bit more difficult to evaluate, and we haven't really managed to delve into this as much as we wanted to. But it gives you still something that is reasonably stable. Again, for dynamics at that kind of speed, a 12% coefficient of variation is still not bad. So we were reasonably happy with that. And here you see a very large increase from the quasi-static because failure is much more sensitive, of course, to strain rate because you're not activating certain dissipation mechanisms in the material when you load much faster. So that's not so surprising. I'll do it.
No, but
Yeah.
10-15 minutes.
Good. So we use that in different configurations, what we call the angle stress gauge equation. So now we refine that by, instead of putting the fibers either longitudinally or vertically, we put them off axis. So at a certain angle, alpha here, to try to enrich the test and not only obtain the transverse modulus, but maybe also the shear modulus at the same time. So get more information from a single test. And now we rely on the angle stress gauge equation. So now this is the subsystem on which you're going to write quasi-static dynamic equilibrium. And so you have the average of the shear stress along that slice, which relates to the average here of the acceleration in the one coordinate system, so the one axis, which is parallel to the fiber, which again you can get from your measurements. You measure in the global coordinate system, and then you just do a vector rotation. And you can also have sigma 2, which this time depends on the component of acceleration perpendicular to the fiber. And you can rework your stress strain curves from that using an off-axis configuration. So that was the PhD of Sam Parry, and we got some nice results. This is an example here on a 45-degree configuration. This is sigma 2 versus epsilon 2. And again, a lovely linear elastic loading, unloading here. And in shear, so again, comparing to the kind of things we could see in the literature, this is immensely better. In shear, you see that it's a bit more messy, but that's not surprising because it's well known that in quasi-static, the shear stress strain behavior is highly nonlinear. Now, at higher rates, it is less nonlinear, but nonetheless, it is nonlinear. And you can clearly see here that at about 1% of strain, you see a flattening of this curve that indicates probably the onset of damage. Interestingly, if you fit a curve to the unloading part of the test, you see that it seems to unload on a slightly different slope. And again, that probably indicates the presence of damage. So I'm still in the process of trying to identify a couple damage plasticity model on these curves. The latest effort was to push it yet further. So here we've got the two components, 2,2 and 1,2. But can we get the 4 orthotropic stiffnesses component on just one single test? It's a bit more challenging, particularly for carbon composite, because getting the fiber modulus is a real nightmare because it's so stiff. On the other hand, the fiber modulus isn't very strain rate dependent, so you could just do a quasi-static test, probably enough. But for a glass epoxy, for instance, it might be interesting. And so we've devised this partial height impact IV. So again, another degree of freedom to try to get more heterogeneous stress and strain fields to obtain more information. So this is the kind of images you get. You can see here the specimen being impacted. So it slightly rotates as well, which also creates some more difficulties for the measurements. And then we're able to identify, I'm going to go quickly, but we managed to identify values that are reasonable for this kind of material. Q22 is a bit too low from what we expected, but there's some systematic errors. So this is preliminary results, and we still need to do a little bit more work on this. But it just shows how you can enrich the test by just changing the configuration, and you could really be very creative. In terms of fracture as well, you now have fracture happening in the combined state of transverse tension and shear, and you could, if you could read them, again, a bit more difficult here, but you could populate a failure envelope. So we haven't done that yet, but it's something that we would love to do. I also had a PhD student who were extending this to interlaminar properties. So these are notoriously difficult to obtain, even in quasi-static, because you have to cut specimens in the full thickness plane of a thick plate. Then you have to pull on it. It's an absolute nightmare. While here, in a way, the test is nearly, well, it's simple to do. Simpler to do. We just cut a specimen, bond it on our waveguide. So we need a mini waveguide and a mini impactor this time. And we have exactly the same analysis. And Jared also devised the shear equivalent, where this time we rotate the specimen, we put it vertically, and the little bit above here actually sees a shear wave. So this is an example here. You see the gamma XY. So this is the free edge at the top, which has 0 strain always. And you see here the shear building up. And you can again build shear stress strain curves at quite high rates with this. So this is all published if you're interested. One of the first things we tested was tungsten-carbide, and I'm just showing this because it's quite spectacular, the kind of force level you can reach. This material is much, much stiffer, much heavier, and much stronger. So you see here we're reaching now 1.5 gigapascal of stress. And it fractures in tension here at about 1.2 gigapascal. But we're only firing here at, I think it was 40 meters per second. With a sharp contact. I think we use steel projector here to have a rise time that's a bit faster. And we produce massive acceleration levels. And we produce here, I think the force here at the maximum of the compression curve is about 200 kilonewton. So it's absolutely incredible the kind of forces you can generate thanks to inertia. If you recover the specimen, it's quite interesting. You get a nice jigsaw puzzle. And so I went in the lab once when the tests were done, and I quite like jigsaw puzzles. So I took all the pieces from the captive chamber and reconstituted the specimen. So obviously it fractured in all sorts of ways. But it was interesting to see that at the end of the imaging time, because we can't image further, we recovered 3 of the cracks that we could see here. Whether these cracks afterwards happened because of the waves or when the specimen crashes in the capture chamber, we don't know. Lloyd, who had a fellowship to explore the high strain rate behavior of bone, also did some very nice tests on cortical bone on the transverse and longitudinal direction. So again, using the mini waveguide and the mini impactor with very nice stress strain curves. And again, a quasi-brittle fracture happening in tension at a wave rebound. So what you see here is obviously the fracture is much messier than what you have in a composite, because the material has an architecture that is much more valuable. But the data was quite nice. We did some tests on adhesives as well, because adhesives are extremely difficult to test, again, because they're quasi-brittle, particularly in tension, it's really hard. And so this is more difficult because now you need to evaluate strains in a very narrow band of the material here. So this is obviously smooth. So you have to take into account the smoothing in the analysis. I don't really have time to elaborate, but this produced some interesting data. We haven't published that, unfortunately. I still have data to process. And recently we published a paper where we extended this for elastoplastic material. And now in this case, you need to use a full inverse identification using the virtual fields method. I don't really have time to go into this. But basically, you're building up plastic spray. So it's a bit like a Taylor impact test, basically, except that it's reverted. And you're using, again, stress from acceleration and stress from strain and elastoplastic model to build up a cost function that you try to minimize. Okay, so this was for the IB test. I'm now going to spend a little bit of time on the IBUS test. So in this case, we're now bonding a specimen on an ultrasonic tonotrode, and we're going to shake it inertially in the ultrasonic range. So here it's a power ultrasonic tonotrode, so it operates at 20 kilohertz. In this case, this is the setup. So you see the sonotrode with the specimen hanging down here. The sample, the flash, the HPVX camera. Here, because it's steady state variation, obviously the illumination is less of a problem. You trigger the flash, then you trigger the camera whenever you have time. So it's much less stringent, much easier to do in terms of experiment. And then this is a typical film. And the video is working. You just have to, if you watch the bottom of the specimen, you will see it move a bit. This is a magnified view. You see that it moves. It doesn't move very much, but it's enough for us to capture the deformation. And what you do when you process the grid for displacement is you basically see here a first mode of vibration with the ends moving up and down with no strain and maximum strain in the middle. So this is a view of the strain field for one ultrasonic run. So you see strain 0 at both ends and maximum in the middle. The strains are much lower here, typically 1,000 microstrain. This was for PMMA. What is interesting here, this is a thermogram, but obtained at much lower frame rates, because we didn't have a high-speed infrared camera at the time. But that's for the 7 runs. So you see here, this is second incrementing, here it's microseconds. So you see that each time we press the run button, so we did 7 runs with increment of power of the solenoid, you see that the specimen heats up. And basically, in a couple of seconds of test, you can melt PMMA. There's just so much heating up in the middle, we reach 100 degrees C very quickly. Now, the interesting thing with this test is that if you pile up these runs one after the other without the specimen cooling down, what you have is you have in each section a different temperature. And so it's like an accelerated DMA test. Along the length of your specimen, you have different moduli, so you can analyze the modulus in the same way as we did for the ID test for each section. And each section now has a different temperature. So what you can get is you can get stress strain curves at all these different locations, calculate the modulus and the tangent delta, and report that in a plot that gives you temperature, strain rate, and modulus. Okay. So you see obviously that the modulus increases when the decreases when the temperature increases. We didn't see very much. I mean, this might be a bit deceptive. You have the impression that there's a variation along the strain rate. If you do an uncertainty analysis, it's not so clear. But this is something we would need to improve with improved measurements. The 10 delta, same thing. You can see a very clear increase of 10 delta with the temperature. With strain rate, it's much less clear. So it's like a very fast DMA test. We adapted this to an off-axis composite as well, and that was reasonably successful. Now, using the off-axis stress gauge equation, you can get a stress strain curve for both transverse stress and shear, and you obtain the two moduli in this one single test at strain rates that, in this case, are more in the order of a few tens of second minus 1. This is a nice video, I quite like it. This is the IBUS test on a bonded joint. You see the specimen, it consists of two pieces of aluminium bonded with an epoxy glue. And if you leave it for a second or so, the bond line fractures and the specimen jumps up. This is actually a cohesive failure. We did the same with a carbon epoxy bond, and it was much less impressive. And so the idea behind that was that maybe we could actually get the fracture toughness by just measuring the kinetic energy that is released at fracture, and that is making the top part jump up. But we never came down to doing this. But I quite like these little videos. And then finally, we're looking now at soft materials. So that's part of a larger project on ultrasonic surgery tools, and we test PDMS as a surrogate for cartilage. So the wave length, of course, here are much smaller. So you see the specimen is tiny here compared to the solid rod. And now the difference is we don't have established waves anymore, vibration. We have traveling waves. So this is typically what the simulation gives you. This is the width of the specimen, and you see that the deformation, the waves damp out very quickly because this has massive damping. And experimentally, we were able to capture that with our high-speed camera. So qualitatively, you can clearly see this wave going positive, negative, and then damping out very quickly. So we are in the process of refining now this test to obtain material properties at strain rates that are relevant for ultrasonic surgery. Okay, very quickly to finish the IBUS test. What am I doing? A little bit over time. I'm going to go fast. There's much less on this one. So here the idea is that we are going to use a fracture to generate a release wave to load the specimen at high rates. So you can see here, this is the long specimen, and the specimen has a notch here. So you put that in a tensile machine, you load it up, and at a certain point, it will fracture because you have a stress concentration. And when it fractures, what you have is you have a compression release wave that travels down the specimen. And if we can capture that with a camera, then we basically have built a very cheap impact machine. So this is the experimental setup. One of the tricks is the triggering, of course, because you have to make sure. And unfortunately, the thing you cannot, you can post-trigger the camera, that's easy, but you can't post-trigger the lighting. And so because we don't know when it's going to happen, and we only know when the break happens, we have to have a specimen that is long enough so that the wave traveling down to the field of view is on the order of the rise time of the flash. So that's a slight downside. But never mind. So you see here the test machine, the long specimen, the camera, the flash. And at the top here, you can see the notches, and there's a little tape here, copper tape, that we use for triggering. When the specimen fractures, it tears the copper film and sends a trigger signal. And then that's the start. So you see, this is the video, and you will see the wave coming down from the bottom. But it's actually a bit difficult to see because it doesn't deform very much. But and it's very slow. We produce very boring high-speed videos. But if you process the images to get displacements, then what you get is, again, the strain here, the acceleration here. This is a section in which we plotted the stress strain curve with the same analysis as we did for the IBUS test. And this is what I had in mind for the bar, what we discussed for lunch. This is very close to the configuration we were discussing. So you see that the release wave enters the field of view, traverses it, and then from there, we can build this stress strain curve. So it doesn't look very spectacular here. Strain rates are intermediate between the IBUS and the IB test, more like in the hundreds of per second. But that also pretty much depends on the sharpness of the fracture. And we get a modulus that is, again, space resolved. The average here is on the order of 5 gigapascal compared to 3 gigapascals in quasi-static for this type of PMMA. And we can also get Poisson's ratio, but I don't really have time to elaborate. This is all published in experimental mechanics. The interest of this test is that it uses a standard test machine, but more interestingly, it can provide low rate and high rate stiffness on the same specimen. Because what we didn't do here is we could have put standard cameras and measure the deformation all the way quasi-statically to fracture, and then it cracks, it unloads, and then we capture the dynamic behavior. And I think this would be particularly interesting for biological tissues and particularly for bone. Because if you look at the data in literature, modulus for bone at high rate and low rates, you have both material variability, interpatient variability, and also test variability. If we could do that on the same specimen, we could basically totally separate interspecimen variability to obtain the strain rate variability. So that would be particularly useful. The other thing we could do is we could rethink about the this composite test to get all the stiffnesses in one go, and again have a more complex shape, measure the deformation quasi-statically, get the unloading wave, and get the whole set of orthotropic stiffness components from the same specimen at low rate and high rate. So in one test, you basically replace something that looks like at least 8 tests if you do it the standard way. But we haven't done that yet. Okay, just a few words of conclusion. I'm going to go fast because I will run a bit. But we devised these 3 configurations. In fact, there are probably many, many, many more. When you have understood the idea behind this, how you get stress from acceleration, the design space becomes quite large. The idea is to use acceleration as a load cell, and it's actually quite powerful because all the information is embedded in your images. You don't need anything else. Regardless of what happens outside, everything is embedded in your images. That's quite powerful. And the kind of data we got for quasi-brittle material, I think, is absolutely incredible. But I mean, we'll refine it quite a bit, but I don't think that I've seen anything like this in literature. In terms of perspective, as I said, test design is a big thing now because the design space is really, really very large. And depending on the type of material testing, the model, you could be really creative. For instance, I don't know usually if you've seen the work, but for elastomers, Clive Fever has done a series of very nice work using this idea in different configurations to get high rate behavior of rubber. Very, very nice work. So in terms of test design, one way of exploring the design space rationally is by using synthetic image deformation, like a virtual twin, plus optimization algorithm, shape optimization algorithm, to try to obtain optimal configurations that take into account the limitations of the cameras, the temporal and the spatial limitation of the cameras. So we published with Michel Reillac a review paper in 2021 on where the state of the art is in terms of this type of test design, but there's a lot of work to be done in this field now. A number of things that would be nice to look at, obviously non-linear behavior, anisotropic plasticity would be something also quite quite funny to do. Heterogeneous materials, now that's quite challenging because, as you have seen, we lack spatial resolution. So we probably need to have something that sort of finite element assisted procedure where we could estimate the sort of low pass filtering effect that a measurement has by itself. High temperature is something we haven't done, but nothing would prevent us from putting a high temperature system in our impact chamber. But I think one of the biggest challenges is whether we will be able to produce new standards in the future that rely on this kind of methodology, camera-based. And there's a lot of work to do. So I've launched a VAMAS group called Material Testing 2.0, and we've already launched one group on anisotropic plasticity, led by colleagues in Portugal and Belgium. But I'm toying with the idea of launching one on the dynamic behavior of composites, stiffness, identifying stiffness components of composites at high strain rates. But we'll see if I can find enough candidates to participate. Okay, this is the unavoidable sponsor slide that concludes my talk. Thank you for your attention.
Thank you for the very nice presentation, and the floor is open for questions.